Hello and welcome to the latest screening in our Kent Thinks Discovers series, where we explore some of the pioneering research being carried out at the University of Kent. Today we go on a journey nearly 500 years in the making to find out how a team from the University of Kent devised and put on display using a special chemical technique to display the famous Tudor warship, the Mary Rose. Later on, I'll be talking to Professors Eleanor Schofield, Alan Chadwick and Fred Mosselman about the film and how science and heritage has saved what has been likened to Britain's version of Pompeii. As ever, we welcome you at home to send in your questions on our live chat panel on YouTube and on Facebook. And as we're all social distancing, do bear with us if we have any technical hitches. And also another note, obviously, it's Clap for Carers at 8 o'clock this evening, so we will be cutting for a short break during then. That's all from me from the time being. We're here now is Mary Rose, A Chemical Conundrum.
For more than 30 years, the Mary Rose ruled the seas until her sinking in 1545. Almost 500 years later, she was raised from the seabed. It was another 2 decades until the University of Kent became involved in the ship's conservation. In 2004, Professor Alan Chadwick was asked by the Mary Rose Trust to lend his advice to solving what was called the sulphur problem.
What we learnt from the early experiments is that the sulphur oxidation, the dangerous compounds, were more at the surface than in the depth of the wood. We also learnt that the sulphur problem was worse the nearer the samples had been taken from a piece of metal in the wood, iron in particular. So where there'd been an iron nail in the wood, which will have completely rusted away, there was a build-up of the sulphur problem.
For many of the Mary Rose's artefacts, it was a race against time to prevent them from degrading any further. Together, the Mary Rose Conservation Team and the University of Kent's researchers, led by Professor Chadwick, carried out experiments on samples from the ship using powerful X-ray producing machines called synchrotrons to reveal the extent of the damage caused by the seawater. Professor Eleanor Schofield joined Professor Chadwick's team in 2009, and here at the UK's National Synchrotron Facility, she's helped develop a programme of experiments where the status of the ship and its many artefacts can be monitored in real time.
Some of the issues we saw with the artefacts, particularly with the wooden artefacts, is that you would see salts develop on them. This is when they were exposed to air and humidity, and sometimes with elevated temperature too. And these salts would form, and they don't look very good, but they also can be very damaging to the artefacts. So what we wanted to do using diamond was to understand how they were formed and how they would develop over time, and then to develop treatments to try and solve that problem. When I first started working at the Mary Rose, we were particularly focused on preparing the ship for drying. It had been through a conservation treatment, and then we had to expose it to air to dry it. In doing that, we knew that we could cause some transformations of all the elements that were in the wood. So we set up a program of work with Diamond Light Source to take samples from the ship, bring them here, analyse them to understand what was happening.
Electrons are sent round a ring at effectively the speed of light. These electrons produce light, which can then be directed down passages known as beamlines, and in turn used on experiments like those on the Mary Rose. The whole system can be compared to a ring road with dozens of slip roads coming off it. It is down one of these slip roads, beamline B18, where the Mary Rose experiments have taken place.
In the case of the wood that we studied, Mary Rose had a couple of important components that are critical for determining the degradation processes. One is the sulfur and the other one is the iron. And the combination of the two is leading to, in a very long term, thanks to the exposure to oxygen, to the degradation processes. On B18 we can select the wavelength of the X-rays to correspond to the excitation of sulfur only or to the excitation of iron only. So we can study the chemistry of sulfur and the chemistry of the iron. The chemistry means, in our case, understanding what is the oxidation state, so how many electrons have been pulled out of the sulfur or the iron, and also the geometry of atoms that surround each of the absorbers that we have chosen.
I think some of the benefits of having a synchrotron, it enables you to penetrate in really small detail and look at the actual chemistry of individual elements, which you can't do with a range of other techniques, and that has enabled the conservation tactics used on the Mary Rose to developing both new methods and verifying methods in terms of what works, what doesn't work, what's most cost efficient, which is always a factor when treating large objects. So it's been very effective in helping preserve the ship.
If you think about it, the whole collection has essentially been marinating in seawater for nearly 500 years. So there's loads of stuff in it that you wouldn't find in normal kind of terrestrial or your everyday objects. So wood normally wouldn't contain these things, but you find all these elements from the seawater lodged in there in different forms. And what this facility allows us to do is to look how they change over time and then develop treatments to protect them for the future.
Thanks to the discoveries made during these experiments, the University of Kent researchers and the Mary Rose team were able to develop a special compound to treat the ship's timbers and artefacts.
We developed a method of making small nanoparticles of strontium carbonate, which we could soak into the artifact. These nanoparticles would react with any acid and essentially neutralize it. And they would sit there as a reservoir. The nanoparticles would be a reservoir that could mop up any sulfuric acid that formed over time.
Really what we were doing here was wanting to prove the chemistry, because this isn't really an ideal way in which we would apply it to the ship. So once we'd proved the concept worked, we then started looking at different application methods, and that's really some of the work that we're doing now, finding ways that we can incorporate the nanoparticles into different ways to get them into the wood.
The results are on display at the ship's dedicated museum. First opens in 2013 and then again after a major revamp in 2016, the Mary Rose Museum welcomes up to 250,000 tourists a year. Many point to the quality of the conservation work in enhancing the visitor experience.
It's really a fascinating collection because it really gives you that personal insight into day-to-day life in Tudor times. It wasn't just a warship, but it was where the crew members lived and worked day to day. So alongside weaponry, you also have very personal items, things like nip combs, shoes, clothing. So it really gives you an insight into Tudor life. Without all the conservation work, these artefacts wouldn't be here and they wouldn't be on display. And it's something that people find absolutely fascinating, that these artefacts are real. They were under the water for all of that time. They've then been raised and you know, through the conservation work, been preserved and put on display for people to enjoy and to view.
Preserving and presenting the thousands of artefacts in such a pristine condition has been central to the museum's popularity.
I think people have in their mind what the old museum used to be like, what the old ship hall was, and when they get here they're just absolutely blown away. If you have a look at our TripAdvisor reviews, you notice a lot of the comments that people are just absolutely blown away by what the museum looks like and the views of the ships and the artefacts now. And I think that really spreads. You know, people tell their friends and family, you must go see the Mary Rose. It looks absolutely incredible.
There's a growing focus at the museum on highlighting the various processes involved in the conservation, with a view to include more of this information in outreach projects.
If you have a look at our family groups in particular when they come to visit, really there's something to interest all ages, and what's really fascinating is how interested the children are. You'd say, well, how come the Mary Rose is here? How did it get here? It was underwater and then it was raised. And just watching them as they go around the museum and learning about the conservation process and all what went behind.
Specifically important to me is that people understand the amount of science, technology and engineering which are absolutely crucial for this collection. And that's not just now, it's been all the way through. It goes back to them finding the ship, excavating the ship, developing conservation treatments, developing this museum we're stood in now, developing the system that's drying the ship. It's just been absolutely crucial, and it always will be. And it's nice to get that message across to people and to give some people an idea of the range of jobs that you can have from STEM subjects.
Going forward, Professor Schofield, along with the team at the Mary Rose and their partners at the University of Kent and Diamond Light Source, will continue to develop a range of techniques for treating the artefacts, including the ship's bricks.
The issues that we see with the salts in the wood, we are starting to see in other materials. One of those is the bricks. So we have bricks in our galley and also used for some ballast. And what we've seen now is that you are getting these crystals forming on them. So we've traced those back to being a similar source to what's happening in the wood. And so now we're doing some work with the University of Kent to really understand what they are. Again, once we understand what they are, we can start to create ways to mitigate against them causing any damage.
The journey of preserving the Mary Rose in recent decades has been underpinned by pioneering science and technology. For the first time, the degradation and treatment of materials in the artefacts has been monitored in real time. This research contributed to the discovery of a special compound to treat the pride of the Tudor fleet, which in turn has enhanced the experience of visitors wanting to get a taste of life on the high seas nearly half a millennium ago.
Everything that we do in the conservation department and all of the research that we do is to make sure that that collection remains stable for as long as possible so that people can come to the museum and immerse themselves in Tudor life.
The problem posed by the complexity and the nature of the material itself that has helped us also to provide new techniques to be able to push a bit, our technology.
The museum is designed obviously to be interesting to all ages, and what we really hope is that we inspire those children as they grow up to keep returning, and obviously as they grow up bring their friends and their family back. It's not just here for us today, it's here for everybody in the future.
That was Mary Rose, A Chemical Conundrum. And if you're just joining us, we will be playing that again at the end of the live Q&A. And I'm delighted to say I'm now joined by Professors Eleanor Schofield, Alan Chadwick and Fred Mosselmans to talk about the film and also to answer your questions that you can send in on our YouTube and Facebook live panels. So keep those coming in during the course of the Q&A. Professor Schofield, let's start with you. You work in, day out at the Mary Rose Museum. Why do you think it's a site that still captivates us to this day?
I think there's so much in the collection. Alongside the ship, we raised over 19,000 objects. And one of the things that I really love about our collection is it captures everybody that was on board. If you think typically with a lot of museums or collections, it'll be the kind of more expensive, the higher people in society, their items that would have been saved. But this is everybody. And I mean, I've worked there for nearly 8 years now, and I still learn things about the collection pretty much every day because there's just so much there. So people, they go one time, but there's no way you can take it all in one visit. There's always a reason to go back and explore further.
It was amazing when we got to go film there, and like you said, the sheer volume of artefacts giving that real taste of Tudor life. Professor Chadwick, you've been the driving force behind this project and the connections between the University of Kent, the Mary Rose Museum and Diamond Light Source. We heard a little bit about that kind of that collaboration between all of the groups, but give us a little bit of a history of how everyone came together.
Well, it started because the Mary Rose had seen some work using synchrotrons on historical artifacts. And they came to me as an expert in synchrotron radiation to ask how they could use them. So I got them in touch with other scientists, with synchrotron staff, and essentially got them going, and then got very much involved in helping them interpret the experiments. And that's been very fruitful because most of my research has been in basic chemistry, very difficult to explain to somebody, but this is really good. You can explain it to people, and you know it's got a long-lasting lifetime. It's something for keeping the past for the future.
And we got a real flavour in that film about, as we were saying earlier, Professor Schofield, about Tudor life. Professor Mosselman, let's come to you. We saw that amazing complex at Diamond Light Source. Could you give us maybe a flavour of the day-to-day lifestyle there, what goes on at the synchrotron facility?
Well, obviously it's very different at the moment, but in past days, like before March, well, we get a range of users. So there are 32 different experimental setups around the synchrotron, and they all operate at the same time. And so we have a number of users from largely the UK, but also all over the world, who come and do their experiments there for between, say, a few hours for some users to 6 days for other users. And so you've got a mass of different scientists looking at different techniques, biologists, physicists, chemists, all sorts, trying to use the X-rays and other light from the synchrotron to help solve their problems.
You talked about a range of scientists and individuals there all working together, and we saw tests on the Mary Rose being carried out in the film. What for you has made the Mary Rose project really stand out? We were talking the other day about just the sheer length of the project, how long it's been going.
Well, I think the length of the project. So like I've started, I think, working with Alan on the Mary Rose project back in 2008, I think it was. And so we've been looking at it for the last sort of 12 years or so. But the other thing is, as sort of Eleanor alluded to, and Alan alluded to, it's really easy to explain to the public. So it's a really high, when we have a lot of open data at Diamond, so the public can come and look at what we're doing, and it's sort of real world problems, so it's easiest to understand, to persuade the public that what we're doing is worthwhile. So there's a lot of biology. I'm not a biologist, that goes on at Diamond, so like they're doing currently research into COVID-19. But from my point of view, as a sort of chemist, geoscientist, then having a project that people can look at and they can understand the sort of on the simple science basic, how an acid might attack wood, and saying that we're using these X-rays to try and understand how to stop this process, gives us a good feel for how it's a good way. I mean, it's obviously really useful to conserve the Mary Rose, but also it's really useful from Diamond's point of view to engage the public and show that big science doesn't just do high tech; it also solves sort of problems that you might think had nothing to do with big science.
And you talked about the COVID test, and we're going to come to that a little bit later on in the activity around that. But we got a couple of questions that have come in from YouTube, so do keep them coming in, people. The first one we've got is, will the Mary Rose still be in a condition to be on display in 100 years? I guess, Eleanor, you're the best person to come to, being based there. Could we expect to see the Mary Rose in its current form and those artifacts still here, come 100 years' time?
Yeah, I mean, everything that we do, the whole remit of my job really is to care for the collection, the ship and all the artifacts. And everything we do, from in-house to the experiments we do at Diamond, is to help us look after it and make sure it's going to be there for as long as possible. I mean, I would say that if we talk specifically about the ship, it is in incredible condition considering everything it's been through, how old it is, it's been in the seawater, that's degraded. I mean, we don't do this all the time, but to give you an idea of what the condition it's in, we've walked on parts of the ship because you can't access it in any ways. We obviously are careful how we do it, but it is in remarkable condition. So I would say it would definitely be here in 100 years' time.
That's really good news for future generations to go and get a flavour of that. We've got another question in on YouTube from Susanna. This one for you, Alan. What preparation was done ahead of time to be ready to start the preservation process as soon as this ship hit the air? We heard a little bit about the sulfur problem. So what kind of preparation went on in those early days?
Well, that's more a question for Ellie. I mean, I come into this late in terms of the preservation of the ship. It was already under a program of conservation before I got started. So Ellie can probably tell you more about that.
Yeah. So when the ship was raised,
sorry, Ellie.
So yeah, when the ship was raised and with all the collection, one of the things that were really important was to make sure everything stayed wet. What you don't want with any of the materials really is for them to just suddenly dry out, because that's when you're going to start to see things crack and break, and to have, say, the metals have corrosion and things like that. So with the ship, what was done was it was kept wet for a number of years as a technique was developed, and then it was sprayed with something called polyethylene glycol, or PEG as we call it. And this was put in there to compensate for where some of the wood had been lost. So just to give it a little bit of structural stability when we did come to drying it. So once it had gone through this series of being sprayed with the PEG, that actually happened for 19 years. So it was a long process. We then started the drying in 2013.
And Ellie, are there some artifacts that are easier to preserve than others? We heard Alan talking about the sulfur problem with the ship's timbers. Are certain artifacts maybe easier to look after and conserve because of their chemical makeup?
It's a mixture of things, really. Everything went through a cascade wash, so it would have had water just flowed over it to get rid of any of the debris from the sea or other contaminants, things like that. Some things that were quite straightforward were things like leather and some of the quite thin and flat objects, because it was quite easy to get everything out of there and give it a good clean. Say when you get something like the wood, it's a bit harder because it being really quite porous, there's lots of opportunity for things to get into the wood. Another thing that's notoriously very, very difficult is the iron, so marine archaeological iron, because you get chlorine that gets into it from the salt in seawater. And then when it's excavated and it's exposed to air, and if there's any fluctuations in the moisture around it, you can very rapidly get really damaging corrosion products. So they're some of the worst ones to deal with.
And Alan, coming to you, what has happened with the Mary Rose in developing that chemistry to protect it, and all the research that has gone into it, can that be applied to similar heritage sites? I'm thinking like the Vasa in Sweden.
Oh, it can be used to the techniques, the preservation techniques can be used for the Vasa, but some of them, there are other objects that are attacked by acid. Heritage objects, things like organ pipes, wooden objects, some manuscripts, etc. So this technique could be used widely.
And Fred, as well, you were talking about all the various projects that have been happening at Diamond Light Source, and Mary Rose obviously being quite a standout one. What do you think are the values for those in the heritage sector and again, sites like Mary Rose to be using a resource like Diamond Light Source?
I think it just provides a range of ability to look at the chemistry of particular atoms in a detail that you can't do with lab equipment. I mean, at Diamond, we've done a fairly wide range of research on various forms of degradation in paint, in art pictures, and even sculptures. Because if you take a scraping of paint and you look at it with a synchrotron, you can work out degradation processes that you can't do in a normal lab. So there's a sort of a wide range of cultural heritage institutions that use synchrotrons, not just Diamond, but other synchrotrons around the world, to try and understand what's happening to the various items they are curating, and then how to treat them or how to reduce the damage in some cases where treating them is just too difficult.
Well, we're getting lots of questions coming in, and we're going to try and answer them all in a little bit. But first, we've got a couple of short clips here sent in by Professor Nigel Mason, who heads the School of Physical Sciences at the University of Kent, and also Corentin Renaud, who's a student from France who's worked alongside Professor Schofield. They've told us their thoughts on the film and on the important work that's being carried out with this project.
The Mary Rose is one of those iconic events in my lifetime. I very much remember the day in October 1982, watching it on the television and watching it being lifted out, just appearing for the first time in over 500 years, coming out of the water. And thinking what amazing a tribute that was to the technology and the engineering at the time. Little did I know at that stage that I would be head of school of a department that has done so much to preserve that wreck. At Kent, we have a School of Physical Science. It blends together people from physics and from chemistry, working together on a whole range of topics, applying techniques and applying technologies to a wide variety of different aspects. The Mary Rose is a classic example of that. The work which has been done by Professors Chagres and Schofield at the synchrotron facility in the UK to explore the structure and to look for how it was being gradually, sadly, destroyed, and then to come up with a technique using modern technology, nanotechnology, to actually save that wreck is a classic example of how academic sciences in universities turn their hand to a whole variety of applied applications. So we were extremely pleased and we're extremely proud in the school and in the university in general to have the opportunity to work with the people at the Mary Rose Bust Museum. The fact that at the end of the day, we've been able to preserve such a unique specimen is of immense pride to the school and a tribute to the caliber of the people who were working in it. At Kent, we're very pleased that our chemistry degree couples together basic scientific knowledge, but also with these type of applications, and encouraging our students to go into a whole variety of careers where they can use those skills. Some of our students have gone on to work in heritage projects across the country. And Mary Rose has been the project that perhaps has supported them and encouraged them to think about those types of careers. So at Kent, as I say, we're extremely pleased and very proud to have been involved in this project. We think that it's a legacy to the research of the department, but we're incredibly proud, but also that the school and the university has created a legacy for the country and for generations to come.
I'm currently a PhD student in chemistry at the Sorbonne Université in Paris. I had the chance to be involved in the Mary Rose project during a 4 months internship I did at the museum under Eleanor Schofield's supervision in 2017. I remember contacting her for a placement at the Mary Rose Trust with the aim to learn more about heritage science. The Mary Rose behind a unique object of study, historically and scientifically speaking. I was very motivated to carry out it in its dedicated museum. I contributed to a research project designed to assess the deterioration of Henry VIII's warship, the Mary Rose. This involved preparing archaeological samples for analysis, that is FTIR and XRF spectroscopies, as well as scanning electron microscopy. I also had to perform data analysis and correlation of them to other research results, such as those obtained at the Diamond Light Source. And I'm very glad that this work was able to contribute a bit to a scientific paper. In addition to the scientific aspect of my work, I was lucky to be able to take part to the museum life. As an example, a science popularization activity around the use of analytical techniques. And finally, this is both the scientific project and these extra activities that make this research internship a very, very good memory. Otherwise, it was very nice to work under Eleanor's direction. who made me aware of the research issues involved in saving the warship. I remember arriving in England with a terrible English, but Ellie was kind enough to deal with it, so thank you. And she contributed to the very stimulating, intriguing, and welcoming work environment at the Mary Rose Trust. Throughout this internship, I became aware of a lot of things, and in particular, the cultural impact of science. Also, research can take time. It is necessary to safeguard heritage, and I think the Mary Rose warship is a very good example of this. And finally, I would like just to thank Eleanor again for allowing me to be part of this scientific adventure, which can only have a very beautiful continuation.
Well, thank you to Professor Nigel Mason and to Corentin for sending in those clips. And also thank you to you at home watching for sending in your questions. We've got a few more that have come in. Alan, I'm going to come to you with this question. You might be a little bit biased in answering this one, but we obviously heard your colleague Nigel Mason talking about the School of Physical Sciences. But we got a question in from Lynn, who's asked, as a student interested in collections care, is it possible to work in the conservation field without a strong chemistry background? Now, I imagine you're going to be really pushing the chemistry side of things there, but how valuable do you think it is to have that knowledge, and is it really essential to be going into this field of heritage?
Well, the field of heritage is obviously very big. I mean, I would be biased. I would think a chemistry or physics degree or science degree would be helpful. But I'm sure it's not exclusive. I mean, you again, probably Ellie is more involved with this kind of question of, what people do. I mean, Ellie didn't go into her degree program with her current job in mind. She went in because of her interest in the science subject. What do you think, Ellie?
Yeah, I mean, so my background is in material science, and Alan's right. I didn't remotely think I would end up working where I do. I'm very happy that I do, and I feel very fortunate. It's a really interesting question because it's quite one of the things I love about the field of conservation and the conservators is this massive blend of skills they have, right? That and even sometimes if people think that they maybe don't know the science, they do, because they're working with the materials and they understand how the material is going to react, and they understand how some of the treatments will affect them. And if you watch, I mean, I've seen conservators, and I've gone into the lab to talk to them, and there'll be say a wooden bowl, for example, that's in numerous pieces and is not looking in a very good state, and then you come back later and the magic that they can work with them is just incredible. So it is such a blend of these kind of artistic and scientific skills. But for sure, if you're working and wanting to develop treatments, then having the kind of the science background, chemistry or material science, whatever it is very beneficial.
Maybe to inspire some of those people to go into this field. Fred, we've also got a question that's come in asking, what are the main projects of Diamond Light Source beyond Mary Rose? And you talked a little bit about working on some of those paintings and other heritage projects like that. But for this question that's come in, what are some of those real key marquee projects that Diamond Light Source have worked on?
Well, I guess the main one at the moment, as I sort of alluded to earlier, is drug discovery, and particularly at the moment, drug discovery with relation to COVID-19, where for the last sort of 2 months they've been working trying to look how various molecular fragments interact with the virus molecule to see which particular drugs exist, might be used for treatment. And so there's been a lot of Diamond work goes into understanding this field called structural biology, which is how proteins work, how sort of all the different proteins and enzymes we have in humans and other animals actually work, to look at how they cycle different elements. From a personal point of view, I work a lot in sort of geochemical areas, in particular with people in the nuclear industry, looking at some of the issues of radioactive waste and trying to understand how we can store that safely and also in the long term bury it safely. And then there's a lot of physics work on, say, magnets and molecular magnets, which goes in not quite so direct level, but is the technology that produces new things like hard drives and higher storage chips. So it really covers the gamut of science. And obviously in the chemistry field, there's a lot of work on catalysis. So that's in terms of greening up industry, using less energy to do reactions. In terms of the automobile industry, currently trying to both develop better batteries, so looking at the future of electric cars, looking at the future of hydrogen cars, and also trying to reduce the pollution from our current sort of petrol and diesel engines.
It's such a range that you talk about there, from like you said, automobiles all the way to tackling the coronavirus that goes on at Diamond Light Source. Ellie, what has been the impact of the coronavirus on the museum?
Well, huge. We closed in mid-March, which is just devastating for us. So the Mary Rose is a charitable trust, so we don't get any government funding. Everything that we survive on is from ticket sales and donations, and about 90% of that we make from April to September, which obviously has coincided completely with this. So yeah, we're closed at the moment. I obviously don't know when we will reopen and what form that will take, but obviously we're working really hard towards that at the moment. And we'll just have to rely on people's support to keep us going. Actually, I will just do one slight plug there that we've just put on recently a virtual museum, which has some great clips giving some ideas of some of the stuff that we've done. You can see on our website some of the artifacts we've got, so it can whet your appetite for when we open again.
And that's obviously really important to get across at this time. You know, part of the reason why we're doing these events, because people aren't able to access, the material and the sites like you were talking about, and it's really giving people that chance to experience the museum at this time. You've also been really active, Ellie, in getting the message out about supporting the museum and heritage projects at this time. Why is it so important to keep supporting heritage? We're seeing daily headlines about the government and businesses being cash strapped. Why is it important to support projects like the Mary Rose?
I mean, there's just in all of that, we're lucky in this country that there's so much fabulous heritage, and that draws so many people to us, and also this is such a resource for us to learn from. Like I said, we learn things all the time from our collection, and as you heard my colleague Josephine saying in the clip, the reaction that you get from people, it's a really wonderful thing. And as somebody that works there, sometimes being in the museum, watching people's reaction, it's really special. People are blown away. And I would say that we probably all need that more than ever in our lives right now, and especially over the coming years.
And also, scientists really being at the forefront at the moment in that fight against COVID. Alan, as someone who works in the field of physical sciences, this is obviously a really important area, not just for heritage, as Ellie was talking about, but obviously for those on the front lines and tackling it. Why is it so important, again, to support the field of physical sciences?
Well, the scientists, I would say, just part of the culture, part of society. Nowhere without your science. And backing up what Ellie was saying about that, the museum and the heritage work is just part of our culture. If we don't have that, we don't have a society. And the COVID is having a big effect on us because we can't get into the labs. We're not going to be able to get into our research labs until the 1st of July. So, I don't need to, I hope I don't need to have to explain why to do science. It's the culture.
Yeah, well, we're all hoping, obviously, for this all to be resolved very quickly, and hearing about the importance of heritage and of science at this time, is obviously good to reaffirm that. Now, with a look to the future, though, we've also got another clip that's been sent in by Dr. Donna Arnold from the University of Kent as well, whose research we heard a little bit about in the film is involving looking at the bricks of the Mary Rose.
I first became involved in the Mary Rose project about a year ago. I've been working with the Mary Rose Trust to understand the phases that are present, so the materials that are present in the bricks, so that hopefully we can understand what damage they might cause and then can start to develop methods to protect the artifacts from decomposition or damage in the future. It's a really exciting project to be involved in. You get to play with artifacts that have come from the Mary Rose, and it's a privilege to be able to handle such artifacts that are precious. We only have so many of them. We can't destroy them ourselves to look at them. We have to be careful in the way we choose to analyze them. So protecting our heritage is really important. It helps us to understand the past, but it also helps us to understand how societies are built, which helps us to understand our present and perhaps our future. And this is a really nice thing to be involved in. It means that you're working on science, but you're also working on things that impact emotion. They impact legal protection rights, how we protect our heritage, and other disciplines that look to understand our history or our future. Being a scientist is really exciting. I get to look for problems, I look at puzzles, and then I get to look for solutions and to think of inventive ways to start to look for new things and new understanding. And this is a really exciting thing. And it's really important to remember that science isn't for just girls or for just boys. It's for people who are curious, who want to make an impact on the world as we see it, and an impact in lots of different things, and heritage is a part of this.
Dr. Donna Arnold there. Thank you very much for sending that in. From the University of Kent, I guess we'll stick with you, Alan. We've got another question that's come in saying, what kind of chemical substance do you need to use to best preserve a ship of this type? Well, we heard a little bit about that at the start of the film, Alan. So just remind us about that process that you got to coming up with that reservoir to submerge the artifacts in.
Yes, well, that would really only apply to the artifacts. the preserving the whole ship chemically would be very, very difficult. I think the more recent work we've been doing has been looking at the effect of the air conditioning, controlling the temperature, controlling the humidity. That is more important. And our recent work suggests that they're the key factors. You know, it'd be very difficult to try and do any chemistry on a foot-thick lump of oak. So it's the more recent work that will help solve that problem. Is that clear?
Ellie, how exciting is that? Yeah, absolutely. Ellie, how exciting is that new chapter looking at the bricks? We've obviously seen the cannonballs, we've seen arrows on display, so leather shoes as well. The bricks as well, why are they significant and are going to be as exciting as those artifacts?
What's quite interesting about the bricks is that the problems that we're seeing with them, the source of that problem is the same as what we've seen in the wood. So we're kind of one step ahead in some ways, that we have an idea of what might be there, so we can tailor the techniques that we're using on them accordingly. What's quite interesting with them is then, but it can affect the brick in a different way. It's more of physical damage because the crystals grow and it breaks the brick apart, rather than with the wood where it tends to be more of a chemical damage where we generate these acids that then can degrade the wood. But yeah, it's interesting because you start then, as soon as we started looking at the bricks, realizing there was a problem, I then had to start, looking up brick compositions and thinking how we would, it's always different. We take core samples from the ship, and for this we were then taking salt cell samples and thinking how we had to press them into pellets. So there's always, alongside the running the experiment, there's so much work that goes on before you arrive somewhere like Diamond to think what's the question you're trying to answer, what samples do you need to answer that, how are you going to make those samples, how are you going to put them in the beamline. So it's this massive puzzle of things that then all comes together. So there's always a link between them, but then obviously the different materials, and we've just got so many different materials. So as a material scientist, it should keep me very busy.
And for you, Fred, as well, that must be quite satisfying and a good challenge to have to be working with all of those different materials and using those skills. We've got another question that's come in from YouTube that kind of links with that. So, Fred, does what has been learned from the Mary Rose work provide learning that's been used in other contexts and in other experiments?
I think it probably the development of some of the techniques, particularly at Diamond, because in the early days of Diamond, we used what's known as a microfocus beamline. So that's a beamline that has an X-ray beam as small as about 1/40th of the width of a human hair, and that enabled us to look in very fine detail at the local chemistry of some of the wood and how it reacted with some of the chemical treatments. Not so much to do with preserving the whole ship, but preserving objects, as Alan talked about, like the handles of swords and stuff like that. And because this was some of the first microfocus experiments that we did in the UK, then the way we did those experiments and some of the results led us to do other techniques, other experiments with things as varied as, say, meteorites and space objects, and even sort of tissue samples from human to do with neurodegenerative diseases. And because the Mary Rose was one of the first things that we used on that particular experimental setup, we were able to learn from that how to do some of those experiments better.
And Fred, we're going to sit with you just to say as well, keep sending in those questions. Thank you for all those that are coming in so far. We are going to try and answer all of them during this panel. Now, Fred, you were talking about earlier on about all those coronavirus experiments and the work being done at Diamond at the moment. I imagine that's taking up most of the resource. Are there maybe any other exciting chapters we can look at on the horizon for Diamond Light Source, and any more exciting projects to be coming along that way?
Well, currently at the moment, we're actually only doing COVID-19 related research, though we're going to reopen in June and start doing other experiments, but they'll all be done in a slightly different way, because in the past, like about 80% of our users don't just send us in samples to measure, they actually come and use the facility. And because of the current travel issues and social distancing and the issues of staying in hotels and stuff like that, all sort of experiments for, say, maybe the next 6 months will be done by posting samples then, and then Diamond-based scientists will do the experiments. In terms of new technologies, I guess some of our key focuses are some of the Diamond of the government's primary research aims. So whether that's to do with energy storage, or to do with developing clean energy, or understanding new materials to make lighter, stronger structures, or say looking at, say, we have a high energy beamline that looks at, say, strong materials like alloys that are used to make lighter transport and lighter structures. And so there's a range of different sciences which all have different important aims in terms of the UK's industrial strategy, and Diamond plays a part to a larger or a lesser extent in many of those.
It's a really dynamic industry, and there's so many different tangents that you can go on within the industry. We heard from Donna there about how it's not just for girls, it's not just for boys, it's an industry that's open to all. Ellie, I know that you've also been very outspoken about getting girls to work in the STEM field, and obviously we've heard some of these projects today, not just at the Mary Rose but at Diamond, that it is a really exciting industry to be working in.
Yeah, I think Donna hit the nail on the head, to be honest with you. It is about being curious and wanting to find answers to things. And actually, one of the things I'd say, one of the things that I find really irritating sometimes is people will not think about science. They'll think of it as being like just somebody in a lab following like some prescription to make something, and there's no understanding of how creative it is. You know, Fred and Alan will know when you're at a beamline and you're trying to put these experiments together, the amount of times that you have to then go and build a new sample holder or find something to hold the sample with, or all these kind of things. And it makes it really exciting. And the satisfaction when you've gone through all of this and all the steps I said before of what's the question you want to answer and how are you going to do it to get to that point of finding the answer. When you do find the answer, when you're lucky enough to do that, it's just really rewarding.
Absolutely. Well, I think look to the future, and a real call to arms to be involved in the industry is a fantastic place to end. So thank you all very, very much for joining in, and also thank you all to you at home for tuning in and sending your questions. And you'll have another chance to do that next week. We'll be back on Tuesday, the 2nd of June at the same time with the next in our series, Peru, A Living Memory, in which we will be looking at a Latin American historian from the University of Kent and the work she's been doing to help Peruvians and identifying with their national identity and exploring that. So we'll have all that to look forward to next week. But if you missed it at the top of the programme, we'll be playing Mary Rose, A Chemical Conundrum again. It just leaves me to thank Professors Eleanor Schofield, Alan Chadwick and Fred Mosselmans for joining us this evening and answering all your questions. I'll be back next week. Thank you very much for joining us, and good night.
For more than 30 years, the Mary Rose ruled the seas until her sinking in 1545. Almost 500 years later, she was raised from the seabed. It was another 2 decades until the University of Kent became involved in the ship's conservation. In 2004, Professor Alan Chadwick was asked by the Mary Rose Trust to lend his advice to solving what was called the sulphur problem.
What we learnt from the early experiments is that the sulphur oxidation, the dangerous compounds, were more at the surface than in the depth of the wood. We also learnt that the sulphur problem was worse the nearer the samples had been taken from a piece of metal in the wood, iron in particular. So where there'd been an iron nail in the wood, which now will have completely rusted away, there was a build-up of the sulphur problem.
For many of the Mary Rose's artefacts, it was a race against time to prevent them from degrading any further. Together, the Mary Rose Conservation Team and the University of Kent's researchers, led by Professor Chadwick, carried out experiments on samples from the ship using powerful X-ray producing machines called synchrotrons to reveal the extent of the damage caused by the seawater. Professor Eleanor Schofield joined Professor Chadwick's team in 2009, and here at the UK's National Synchrotron Facility, she's helped develop a programme of experiments where the status of the ship and its many artefacts can be monitored in real time.
Some of the issues we saw with the artefacts, particularly with the wooden artefacts, is that you would see salts develop on them. This is when they're exposed to air and humidity, and sometimes with elevated temperature too. And these salts would form, and they don't look very good, but they also can be very damaging to the artefacts. So what we wanted to do using diamond was to understand how they were formed and how they would develop over time, and then to develop treatments to try and solve that problem. When I first started working at the Mary Rose, we were particularly focused on preparing the ship for drying. It had been through a conservation treatment, and then we had to expose it to air to dry it. In doing that, we knew that we could cause some transformations of all the elements that were in the wood. So we set up a program of work with Diamond Light Source to take samples from the ship, bring them here, analyse them to understand what was happening.
Electrons are sent round a ring at effectively the speed of light. These electrons produce light, which can then be directed down passages known as beamlines, and in turn used on experiments like those on the Mary Rose. The whole system can be compared to a ring road with dozens of slip roads coming off it. It is down one of these slip roads, beamline B18, where the Mary Rose experiments have taken place.
In the case of the wood that we studied, Mary Rose had a couple of important components that are critical for determining the degradation processes. One is the sulfur and the other one is the iron. And the combination of the two is leading to, in a very long term, thanks to the exposure to oxygen, to the degradation processes. On B18 we can select the wavelength of the X-rays to correspond to the excitation of sulfur only or to the excitation of iron only. So we can study the chemistry of sulfur and the chemistry of the iron. The chemistry means, in our case, understanding what is the oxidation state, so how many electrons have been pulled out of the sulfur or the iron, and also the geometry of atoms that surround each of the absorbers that we have chosen.
I think some of the benefits of having a synchrotron, it enables you to penetrate in really small detail and look at the actual chemistry of individual elements, which you can't do with a range of other techniques, and that has enabled the conservation tactics used on the Mary Rose to developing both new methods and verifying methods in terms of what works, what doesn't work, what's most cost efficient, which is always a factor when treating large objects. So it's been very effective in helping preserve the ship.
If you think about it, the whole collection has essentially been marinating in seawater for nearly 500 years. So there's loads of stuff in it that you won't find in normal kind of terrestrial or your everyday objects. So wood normally wouldn't contain these things, but you find all these elements from the seawater lodged in there in different forms. And what this facility allows us to do is to look how they change over time and then develop treatments to protect them for the future.
Thanks to the discoveries made during these experiments, the University of Kent researchers and the Mary Rose team were able to develop a special compound to treat the ship's timbers and artefacts.
We developed a method of making small nanoparticles of strontium carbonate, which we could soak into the artifact. These nanoparticles would react with any acid and essentially neutralize it. And they would sit there as a reservoir. The nanoparticles would be a reservoir that could mop up any sulfuric acid that formed over time.
Really what we were doing here was wanting to prove the chemistry, because this isn't really an ideal way in which we would apply it to the ship. So once we'd proved the concept worked, we then started looking at different application methods, and that's really some of the work that we're doing now, finding ways that we can incorporate the nanoparticles into different ways to get them into the wood.
The results are on display at the ship's dedicated museum. First opened in 2013 and then again after a major revamp in 2016, the Mary Rose Museum welcomes up to 250,000 tourists a year. Many point to the quality of the conservation work in enhancing the visitor experience.
It's really a fascinating collection because it really gives you that personal insight into day-to-day life in Tudor times. It wasn't just a warship, but it was where the crew members lived and worked day to day. So alongside weaponry, you also have very personal items, things like knit combs, shoes, clothing. So it really gives you an insight into Tudor life. Without all the conservation work, these artefacts wouldn't be here and they wouldn't be on display. And it's something that people find absolutely fascinating, that these artefacts are real. They were under the water for all of that time. They've then been raised and you know, through the conservation work, been preserved and put on display for people to enjoy and to view.
Preserving and presenting the thousands of artefacts in such a pristine condition has been central to the museum's popularity.
I think people have in their mind what the old museum used to be like, what the old ship hall was, and when they get here they're just absolutely blown away. If you have a look at our TripAdvisor reviews, you notice a lot of the comments that people are just absolutely blown away by what the museum looks like and the views of the ships and the artefacts now. And I think that really spreads. You know, people tell their friends and family, you must go see the Mary Rose. It looks absolutely incredible.
There's a growing focus at the museum on highlighting the various processes involved in the conservation, with a view to include more of this information in outreach projects.
If you have a look at our family groups in particular when they come to visit, really there's something to interest all ages, and what's really fascinating is how interested the children are. You'd say, well, how come the Mary Rose is here? How did it get here? It was underwater and then it was raised. And just watching them as they go around the museum and learning about the conservation process and all went behind.
Specifically important to me is that people understand the amount of science, technology and engineering which are absolutely crucial for this collection. And that's not just now, it's been all the way through. It goes back to them finding the ship, excavating the ship, developing conservation treatments, developing this museum we're stood in now, developing the system that's drying the ship. It's just been absolutely crucial, and it always will be. And it's nice to get that message across to people and to give some people an idea of the range of jobs that you can have from STEM subjects.
Going forward, Professor Schofield, along with the team at the Mary Rose and their partners at the University of Kent and Diamond Light Source, will continue to develop a range of techniques for treating the artefacts, including the ship's bricks.
The issues that we see with the salts in the wood, we are starting to see in other materials. One of those is the bricks. So we have bricks in our galley and also used for some ballast. And what we've seen now is that you are getting these crystals forming on them. So we've traced those back to being a similar source to what's happening in the wood. And so now we're doing some work with the University of Kent to really understand what they are. Again, once we understand what they are, we can start to create ways to mitigate against them causing any damage.
The journey of preserving the Mary Rose in recent decades has been underpinned by pioneering science and technology. For the first time, the degradation and treatment of materials in the artefacts has been monitored in real time. This research contributed to the discovery of a special compound to treat the pride of the Tudor fleet, which in turn has enhanced the experience of visitors wanting to get a taste of life on the high seas nearly half a millennium ago.
Everything that we do in the conservation department and all of the research that we do is to make sure that that collection remains stable for as long as possible so that people can come to the museum and immerse themselves in Tudor life.
The problem posed by the complexity and the nature of the material itself that has helped us also to provide new techniques to be able to push a bit, our technology.
The museum is designed obviously to be interesting to all ages, and what we really hope is that we inspire those children as they grow up to keep returning, and obviously as they grow up bring their friends and their family back. It's not just here for us today, it's here for everybody in the future.